Hello everyone. So today we're going to go ahead and do some practice problems for Unit 3. Okay. So let's go ahead and begin by looking at this example that we have here. So let me go ahead and hide this panel. And we're going to go ahead and talk about the domain. So first of all, I want you to start thinking, what is the domain? What is the domain referring to? Okay. So go ahead and pause the video. Think about what is the domain. And let's work on this one. We have the following logarithm with a base of 2, and it has all of this right here. So if we think back on a logarithmic function, we can go ahead and see that a logarithm, let's go ahead and draw an xy axis. We can see that the logarithm is the inverse of an exponential. So it should be looking something like this. So very, very close to the x-axis, and then it goes ahead and increases like this. Okay, so we have something that looks like this, and it'll go really, really close to this asymptote about x equals 0. Okay, so what I want you to know is that this logarithmic function is all the numbers that are bigger than 0 on the domain. But in this case right here, it has gone through some transformations, and we can probably identify what they are, but there's also an algebraic method that I went ahead and showed you guys in class. Then it appears that it helped most of us here. So we got 2x minus 1, so I got 2x minus 1, minus 1. And we can see that it's greater than, right? It's greater than all these x values. So it must be greater than the x values 0, right? It's because it's to the right. So we're going to go ahead and solve for this inequality. So plus 1, I got 2x is greater than 0. And I go ahead, whoops, not 0. It is greater than 1. And from there, we can go ahead and solve for this by dividing by 2, divided by 2. So x is greater than 1/2. So pretty much now this transformation's happened. So now this shows that the numbers will be 1/2 all the way to the right, just like this happened. It's going to go all the way to the right, so the biggest number we should have is infinity. And this will also be a parenthesis because the value here now will be 1/2 instead of 0. So it's still vertical asymptote, so our domain will be the following. Okay. For number 2, I'm going to let you guys do this one on your own. I'm just going to go ahead and give you guys a couple hints. So whenever they're asking to solve for an equation like with a log on one side and a number on the other side of the equation, I want you to think about the snail method. Okay, the snail method that we discussed in class that tells us that this base right here, this 2, will become the base of this 3. Okay, so for that one, you can refer to your notes, and that will be okay. I don't think we'll have much difficulties with that. Okay, I'll go ahead and help you guys with this one. And this one's talking about, let's go ahead and use the properties of logarithms to identify, to go ahead and compress it to a single logarithm. Okay, so what I want you to know is the following. Well, actually, I'm gonna go ahead and ask you guys to think about this. When you see subtraction, right? When you see subtraction of logs with the same base, what does that mean? What does that tell you to do? So when you see subtraction of logs, what does that tell you to do? Okay, so hopefully you said that that does division. Now, when you see addition, the sum of logs with the same base, right? 4 and 4. What does that tell you to do when you see addition of logs with the same base? Hopefully you said that was addition, multiplication. So remember, subtraction, I'm going to go to write it right here. Subtraction is division, and addition is multiplication. Okay, so let's go ahead and compress all of this. So keep in mind, whenever you have a coefficient, that is called the power rule. The power rule tells us that whenever you have a coefficient, that becomes the exponent. So in this new case, I got log base 4 x raised to the 1/2 minus the log base 4y plus, remember this is the coefficient right here, so it becomes the exponent as well, so log base 4 w to the third. Okay. Alrighty, so I'm going to go ahead and make this a little bit nicer. Keep in mind that whenever you have x to the 1/2 or a variable to the 1/2 exponent, that is the square root. Okay. So in reality, this right here is log base 4 x to the 1/2. It's the same thing as saying log base 4 square root of x. Okay. The next part says that it is being subtracted. So I'm going to go ahead and have some division going on. Okay. So before I even do that, I'm going to make this log really big so everything can fit. So log 4 big parentheses, right? This was already here. We had already just done it. So I'm going to keep it on the top, square root of x. And I have this subtraction of a y. So there should be a y right here in the denominator. Okay, the next one says that I got plus, right? Plus a w to the third. So that's going to be multiplication. And that's going to multiply times the other part, which was the square root of x, like that. So I should have something like this. I'll go ahead and rewrite it just so it won't look as messy. And we have something like this: square root of x times w cubed and y at the denominator. So hopefully that wasn't bad. If anything, guys, you can go ahead and rewatch the lesson about this one, and everything should come back if you look at your notes as well. Okay. Now, when they tell you to go ahead and expand, you're going to go ahead and write multiple logarithms. So keep that in mind. Right here, we have division. So you should have two separate logs. Keep in mind they must have the same base, right? Okay. There is the next one, so watch out with that. And this w to the square root. So keep in mind that it gives us 1/2, right? It's the same thing as saying power to the 1/2 is the same thing as square root. Okay. Whenever you see something like this, when they talk about the end behavior, it's always nice to go ahead and give yourself a nice little sketch. So I'm going to go ahead and sketch this right here. So keep in mind x, y. And I want you to think about this right here. 2 raised to the x. Is that going to be an exponential growth or exponential decay? Keep in mind, there's two different forms. If we have this base, if the base is bigger than 1, this tells us it's a growth. If the base is between 1 and bigger than 0, that is a decay. So what does 2 raised to the x tell us? Is it a growth or a decay? So hopefully you're able to say that this right here is a growth. So yes, it's going to look like this. All of the growths look like this. Okay. So from here, we can look at this end behavior. So as x goes to infinity, as x goes to positive infinity, keep in mind x is going to positive infinity is this way. So as x goes to the right, what is the y doing? What is the y doing? So as x goes this way, my y's are also going up. So this is going to be positive infinity. Let's look at this one right here. As x goes to negative infinity. Negative infinity is telling us it's going to the left. Okay? So as x's go to the left, as x goes to negative infinity, my y is getting so close to this x-axis that we're going to go ahead and say it's 0. So as x goes to the left, we can see that my y's go really, really close to the x-axis, therefore equaling 0 eventually. Okay, for the next one, I'm only going to go ahead and help you with the parent function of a logarithm. But keep in mind, guys, you need to be able to know these on your own. Okay, so a logarithmic function is the inverse of an exponential. We just saw an exponential that was like the 2 raised to the x from the last example. So we reflected over the line y equals x, we should have this right here. If not, we have it in our notes, or if we use the decimals calculator, we can also get a nice sketch. Then you're doing the same thing. You're finding out what happens as x goes to the right, what is y doing? What happens as x goes to the left, what is y doing? Alrighty, I'll help you out with this one right here, describing this transformation. So transformations work pretty much the same for all functions. It's just a matter of identifying items. So if you were to have a number right here, right, this would either tell you vertical stretch or vertical compression, but we don't. So it's a 1, nothing really affects us. This 1/3 x plus 2. Now, right here is where things get a little tricky because we're so used to having this 1/3 being on the outside. When that is not the case, guys, and it's not explicitly told that has been factored out, you're gonna have to go ahead and factor out for yourself. So in order to do that, the best way to approach this is by factoring out a 1/3 from each individual part. Now, that might look a little complicated, but what you're really doing is trying to factor out the 1/3 by dividing everything by 1/3. So I'm going to go ahead and write it again. Log, there's no base, so you can assume that's 10. So it's going to be 1/3 on the outside. If I factor out from 1/3 x, I'm left with x. And if I factor out 1/3 from 2, that's the same thing as dividing 2 divided by 1/3, which is the same thing as 2. When you divide by a fraction, it's the same thing as multiplying by the reciprocal. So multiply by 3/1, which gave me 6. So plus 6 minus 5. So now it looks a lot nicer, and we can totally see more of the transformations. So this 1/3, if it's inside the parentheses, guys, everything here is horizontal. Now the 3, on the other hand, it does the opposite of what we're thinking. So 1/3 in my head, I'm thinking it's gonna go ahead and be a compression, but keep in mind it's not. It's actually horizontal stretch by a factor of 3. Okay. Now this plus 6 right here, okay, in my head I'm thinking positive 6 is gonna make me go more positive, but it actually is not. So it's actually gonna be 6 units to the left. It did the opposite of what I was thinking. Okay, last but not least, this minus 5 right here, this is not going to lie to me. So a minus 5 is going to tell me to do what? Okay, 5 down. So these right here, I would encourage you to continue studying your transformations because these will not leave anytime soon. Okay. For number 8, keep in mind that you are working with logarithms with the same base that are equal to each other. So whenever you solve this equation, guys, it is as simple as doing, as setting each part, right? You can say pretty much everything got set to the E. And these were identities that tell you that, as you guys were saying in class, cancels, but actually they're inverses of each other, exponential and logs. So you're just left with 2x plus 1 is equal to 4x, okay? So from here, I truly believe you can solve this. So that's as far as I'm gonna go ahead and do. And go ahead and find that solution. Okay, last but not least, we're gonna go ahead and see what is this solution. So what should be the first thing we should do? Okay, so by now you should be thinking about a common base. Okay, so for something like this, we're gonna go ahead and see that this is 1/25 and this is 1/5. Now, stuff like this it's ending with 5, so I'm gonna go ahead and assume that my same base is 5, right? Could there be a better base? For sure, but I'm gonna go with 5, and we're gonna take it from there. Worst case scenario, we just try it again. Now, we're gonna go ahead and see that they already came with exponents on their own, but I'm gonna go ahead and try my best to make sure that they are still equivalent to 5 to some power. So ideally, I have 5, and whatever they came with, x plus 3, and then is equal to 5 to the third. Okay, now I'm not done because I know that this 5 still has to somehow equal to 25. So there should be a missing exponent that accounts for that. And then the same thing goes for here. This 5 needs to somehow be to raise to this power in the red parentheses that will give me 1 over 5. Okay, so let's go ahead and do the first one. 5 to what power gives me 1 over 25. Okay, so for this one right here, I know what 5 to the second is. 5 to the second is the same thing as 5 times 5 gives me 25. So 5 to the second gives me 25, but I don't want 25. I want 1 over 25. So remember the identity? A raised to the negative 1 is 1 over a. So this must be 5 to the second gives me 1 over 25. So minus 2 right here. So this right here is what goes right here. And that's how I was able to figure it out. Okay, let's go ahead and try the next one. 5 raised to some exponent must give me what they had given me in the original, 1/5. So this one's not as bad. I could pretty much look at the property and see that this has to be a negative 1. Negative 1. So now that the bases are the same base, we can go ahead and get the exponents, right? And set them equal to each other. Exponents equal to each other. Now keep in mind, guys, that if that this right here, I forgot what I was saying. Oh yeah, I was gonna say that if you are struggling with this, there's also a more in-detail video that can go ahead and help you out. So let's go ahead and set the exponents equal to each other. So I got x plus 3 times negative 2 on the left hand side is equal to 3 times negative 1. And from here I can go ahead and solve this by distributing my 2 into both terms. So negative 2x minus 6 is equal to negative 3. So far so good. I can go ahead and look at this. I go ahead and add my 6, and I'm left with negative 2x is equal to negative 3 plus positive 6. So it's going to be 3. All I have to do now is get rid of that multiplication by negative 2. So I'm going to go ahead and divide by negative 2 on both sides. So x is equal to 3 negative 2/2. Okay. Awesome. So hopefully that was not such a bad review and you knew most of the problems. If not, if you did struggle with this, I encourage you guys to look at your notes, look at the videos, and hopefully that is a better way to study, if anything. Worst case scenario, you could always message me for help and I'll reach back to you as fast as I can. As always, guys, thank you and good luck.